recording the lecture today so that if there are things you miss as we go along, you can go back and check it out. So probably just like we started in 228, we're going to start off at the beginning with signals. And in this case, of course, discrete time signals. Oh, got one? All right. Yay. Mystery solved. Thank you. I'm going to pass that back. Perfect. Thank you very much. All right. So, signals. Where do digital signals come from? Well, pretty much they usually come from sampled versions of continuous time signals. That could be a speech signal that your cell phone is digitizing and getting ready to send off. It could be medical signals. So if you're diagnosing heart problems, you might hook up an EKG machine and you get these interesting waveforms from electrodes on the body, which might be digitized. Or if you're listening to a stethoscope, to an audio signal of listening to a heartbeat, that can also be digitized. There are digital stethoscopes now that some doctors use. Everything that starts off in the real world as analog can be sampled and turned into a discrete time signal that we can use discrete time or digital signal processing on. And in fact, that's pretty much how it's always done now. But generally, they do come from real world signals or from continuous time signals that are sampled. And by sampling, we mean you take that continuous time signal, which itself can be completely varying to any level. It's defined, it's a continuous signal, so it's defined with probably a single value at any instant of time. So you can parse time down to whatever degree you want. So you could you know, to the point of ridiculousness of defining one exact value with whatever degree of precision you want at whatever time interval you want with a different degree of precision. But it's this idea that it's defined at all points in time. There's no place where you can't define a particular value of the signal. Now, if we take that and look at only certain samples of that signal, and so we'll choose a particular time interval and turn it into, well, a sequence of samples. If this is x of t, we'll call this x of n. Here our independent axis is time. Here we lose track of time. Once we've sampled data, we can get back there if we know some information, but in general, in discrete time world, we're suddenly divorced from time a little bit. We have our signals are represented by just a simple sequence of numeric values. So I've got 1, 2, 3, 5, 6, 3, 2, you know, it's just a list of numbers, which may have started off as samples of a continuous time signal, and probably were. But that means we have information that's relevant only at particular instances of time. I mean, if we took samples of this, we only know what was going on at this instant, and that instant, and that instance. We captured that information, but we've lost everything that's gone on in between. In general, we always use a regular sampling interval, meaning we're always going to use an equal space time between samples. We keep that constant, and we'll call that time the sampling interval, t sub s. So the time between any two samples, that's our sampling interval, t sub s. And we'll keep that consistent. And that's going to be our connection back to the time, to time, excuse me. If we know a sample and we know its index, we can convert that index back to time if we know this sampling interval value, or its inverse, which is the sampling frequency. So we could say that this discrete time version of our signal, x of n, is the continuous time signal, but sampled only at particular values of t that are integer multiples of that sampling period. And in general, we do start at time t equals 0 is our first index 0. At index 1, we're at 1 t sub s in the time domain. at index 2 or over by 2 t sub s, 3 t sub s, 4 t sub s. So t sub s, or its reciprocal, is our connection between the discrete time world back to the real time axis. And n is the becomes now our new index for our discrete time signal on our independent axis. So we'll be plotting x sub n versus n, as opposed to where we were originally, x of t versus t. Now we're going to have to go into a lot of detail about what the implication is of taking just samples of that original continuous time signal and representing it with this sequence of numbers. As you might surmise, how I do that, I could do that poorly, like I could let there be too much time between these samples so that a lot of interesting things happen that I don't see. And that could be a problem. And so we're going to have to look at what criteria do we have to place, what restrictions do we have to place on this sampling interval, or the sampling frequency, in order to do a good job of the sampling. But we're going to put that off till we talk about some basic signal characteristics first. Notation, your textbook doesn't do this, but I'll try to be consistent about it, because we are going to be jumping back and forth between functions that are continuous functions and functions that are discrete functions. And so where we have continuous functions like you had in 228, if I'll use a parentheses for the independent axis unit, and if it's a discrete time function, I'll use the square brackets to tell us, well, that one's discrete time. Right? So whenever we have square, we know that there's probably sample involved. Unitary value is not a continuous function. Now, if I have a discrete time signal like x of n, there's going to be several different ways that we can represent that same sequence of numbers. The most straightforward way would be what your book calls an array representation, where I just put the sample values in a list, in an ordered list, surrounded by braces. And so the braces enclose that ordered list, usually separated by commas. If we put 3 dots at the end, that means we didn't give you all the information. The sequence continues on with non-zero values after these dots. Okay? If I were to leave those dots off and just put the close bracket, then you can make the assumption that this is it. These are all the non-zero values of that signal. Everywhere else it would be 0. So I'll try to be consistent with that, yeah.
So that represent a pattern to infinity?
Not necessarily. This may or may not be periodic. I'd have to tell you, does this period repeat, or is this just kind of keep dying out, or what's going on there? Generally, we assume it's not necessarily periodic unless we tell you, or unless it's kind of obvious. Now, usually in this kind of ordered list, there's some kind of indicator. It's an arrow from above, an arrow from below, somewhere that tells you where is index 0. Because we need to kind of make that connection. And again, index 0 probably was whatever we call time 0 back before we sampled. So generally, another convention is to underline the 0 sample would be the other way that that's sometimes done. Different books have different conventions. But again, once we sample a continuous time signal, we lose our connection, our direct reference of time. We just have an ordered list of numbers. So if you were to able to read the numbers off of a compact disk directly, they would be just a series of numeric values, a bunch of binary numbers, actually 16-bit binary numbers, that represent the amplitude of the audio signal in each of the left and right channels, plus some extra stuff put on top for encoding the information and for helping the recorder track along and find its place on the disk, but just a list of numbers. If you want to get back to the time domain, I got to tell you T sub s, a sampling interval. or again, its reciprocal, and we'll, so T sub s is the sampling interval, and its reciprocal, 1 over T sub s, is we'll call capital S, or sometimes we'll call it F sub s. That's the sampling frequency, or the sampling rate, sometimes it's called that. So this would be seconds per sample, be the units on T sub s, and the sampling frequency is going to be in samples per second. For example, again, using the CD example, the compact disc, the sampling frequency is 44,100 samples per second. And the reciprocal of that would be the sampling interval. Okay? So those two are reciprocals. I got to tell you one of those two in order for you to be able to tie that ordered list of discrete time values back to where they occurred in time. Without that information, once I get into the discrete time domain, all the processing I'm doing, all the manipulation is in its own world. Again, we generally assume that index n equals 0 represents time, the time origin as well. And if that's true, then if I'm at some sample, some particular sample where the index is a value of k, then I know if index 0 happened at t equals 0, then the way I get back to time is multiply k, the index value of my particular sample, by t sub s. That's all pretty straightforward. Okay. A couple couple signals that we run into, and you'll recognize these as the discrete time counterparts to some of the basic signals that we used back in 228 and continuous time systems. We have the unit sample sequence, sometimes called the unit impulse sequence. Some books use a Greek delta of n for that. Your book doesn't like that. It uses a little d of n. And it's like an impulse function, except it's only non-zero at one point. It's 0 everywhere, except at n equals 0, or whenever this argument equals 0. Then it has not an impulse, but a value of 1. But it serves the same purpose as the unit impulse sequence did in continuous time system, but it's simpler. There's none of this weird, off to infinity with infinitely narrow with an area of 1 stuff. It's just 1. And so the name is kind of fitting, a unit sample sequence. So a unitary, one sample with a height of 1 at n equals 0. Now, if I put something else in this argument, then I have a shifted unit sample. Again, I look at where does this argument equal to 0. That's the point where I get the one non-zero point of a height of 1. So if, for example, if k was 3, delta of n minus k is 0 everywhere except at n equals 3 at that point. So it operates shifting by index is similar to time shifting in continuous time signals. And again, as before, the time shift with a x of n minus k implies a time delay, a shift to the right. We have a unit step sequence, looks like a unit step in continuous time, except it's sampled. So it's 0, 0, 0, 0 everywhere up until we get to n equals 0. Then at n equals 0, we go to 1 and stay there forever. And I guess I should have some dots going there. So again, it's like a unit step function that we sampled. We can represent that same signal using unit step sequences and sums of unit step sequences. So here's a summation notation that we're going to use quite a lot. And so this is a sum from k equals 0 to infinity, however many we have, of delta of n minus k. So if we were to write that out term by term, first we put k equals 0 in here, and our first term would be delta of n minus 0, which is just delta of n. But k equals 1, we have delta of n minus 1, delta of n minus 2, plus delta of n minus 3. And so hopefully you would convince yourself that if I added each of these unit sample sequences and their shifted versions, I would get back this step function. We call this the weighted sum of unit sample sequence way of representing a signal. And it's a convention that's going to come in handy when we get to talking about your good friend convolution. It's going to set us up for the way of describing signals that will step naturally into convolution. Is everybody okay with this notation? So we literally just start with k equals 0, plug it in this, add it to this with k equals 1, k equals 2, all the way up to infinity. Now back in discrete time systems, we did this as well, except there was an integral out here. And this was a delta function sequence. And it was a little harder to wrap our minds around. But this we can kind of get more intuitively. Hope. Unit ramp function is like the ramp was in continuous time again, but sampled. It's 0. Well, we assume it's a causal ramp. So it's 0 for n less than 0. And for n greater than 0, the value of the function is the same as the index. So at index 1, it has a height of 1. At index 2, it has a height of 2. Index 3, and so on and so on.
Causal involves 0.
Causal, and we'll get to that too. But causal means that for any index less than 0, it has to have a 0 value. Right? It can be non-zero right at 0, but prior to that, it has to be 0. Okay. If I use that same weighted sum of unit sample sequence representation, it would look like this. It's shifted delta sequences shifted by k, multiplied by k. We have r of n is n. So if we wrote this out explicitly at k equals 0, we would have 0 times a delta of n. Well, that gives me this point. Plus k equals 1 times delta of n minus 1 gives me that point. 2 times delta of n minus 2 gives me that point, and so on and so on and so on. Okay. We're okay with that notation? Making sense? All right. If I wanted to describe this more mathematically in what we would call an analytical representation, well, this is n times u of n. U of n was my unit step function. If I multiply a unit step function times n, the unit step helps me set these guys to 0. The unit step function from 0 on has a height of 1. So this would be just 1 times n, which satisfies this part of the expression. And so this is going to be the more typical way that we'll describe our signals when we can. We'll use mathematical or analytical expressions, functions, generally functions of n, just like we use functions of time back in continuous time signal. We'll want to have an analytical or mathematical description of our signals where we can. And we'll be restricted to using either predefined analytical functions or ones that we have we have to use predefined ones. Okay. We have rectangular pulses, rect pulses, rect of n over 2n, which have a height of 1 for any the absolute value of the indices are less than or equal to this capital N. So it has a width of 2 times n. And it has 2n plus 1 samples. We go down by n, up by n, and we get the center sample. This is an unshifted rectangle function. This particular one would be a rect of n over 4. Would go to minus 2 to plus 2, and has 1, 2, 3, 4, 5 samples. Here we're describing it kind of brute force. Could you write out that rectangle function using unit step functions? The analytical expression. Be careful, this one's a little tricky. Who's got an answer for that? Yeah. Everybody likes that? So we said it's u of n plus 2 minus u of n minus 2. So u of n plus 2 would go minus 1, minus 2, minus 3, minus 4. U of n plus 2. U of n plus 2. So that would start going high there and be that way forever. 1, 2. And then we're going to subtract off u of n minus 2. 1, 2. Which is going to start at here, and there, and there, and there, and there. Okay, we like it still? No. What should it be? Minus 3. I'm going to get rid of that sample and take it back to 0 here. I made the exact same mistake when I set up the slide. So everybody intuitively, and in fact in continuous times where we had to shut things off right away, that was the right answer. But here, in this discrete time world, and it's a little squirrelier. We've got to wait that extra interval before we take out the samples. So yes, this would be an analytical expression. Started here and shut it off back here. Thanks for volunteering that. Okay, we have sinc functions, and sinc of n over capital N, which is 1 at n equals 0. It's 0 at particular points at k at n equals integer multiples of this capital N. And using the one definition, the sinc function would be sine n pi over n, or n pi over n pi over n. And again, just like in continuous time, we've got to be a little careful about what we're calling sinc functions and normalized sinc functions. Is, for example, in some texts, sinc of x, even discrete time with sinc of n, would be sine of n over n, and in others other textbooks it's pi n discrete over pi n. So I'll try to be clear, explicit about how I'm using sinc function if we use the discrete version. I have exponential functions, of course, where x of n is some base raised to the nth power, and usually we'll use causal exponentials, meaning we will look at them what's going on after n equals 0, or from n equals 0 on. If the absolute value of our whatever we're exponentiating happens to be greater than 1, then this exponential is a growing term. We get a squared, a cubed, a to the 4th, and we're going on up. Right? If that a absolute value is between 0 and 1, so it's a fraction, then we have a decaying exponential, where the square is smaller than the original, and the cubic smaller than that. Now, I've got absolute value. What if I had like a negative 1/2 for A. How would this plot change? If I have a negative something I'm exponentiating compared to something positive. It would alternate up and down, right? Go positive, negative. So in the odd powers would be negative, the even powers would be positive, negative, positive, be back and forth, still decaying, but it would be alternating back and forth and oscillating. Okay. Speaking of oscillations, we have discrete sinusoids as well, which are generally sampled versions. Again, this is a slide taken from your text, so they're using the parentheses, but assume those are square brackets. Just some amplitude time cosine. Well, we've got an omega n plus theta. And so now we see we have samples of that sinusoidal signal against an index n now, not time. And we can have exponentially weighted cosines, just as we did in continuous time, which are ones that are decaying or expanding, but hopefully decaying with time. Because I have this u of n, I've got zeros for n less than 0. We have the sinusoidal variation is coming from the cosine. The decaying amplitude is coming from this exponential term. We're seeing the combined effects of exponentiation and the oscillation of the cosine in there. A complex exponential combines those. So we might write it this way, where we have a real exponential term followed by a periodic term. So these are all, this is real terms, exponents, raised to the n power. And here the e to the j omega is also raised to the n power, but there may also be a phase, which we'll add on there. So we have kind of a real part and a periodic thing going on here, which I can rearrange the exponentials into a x of 0 e to the j theta, which you might recognize as a phasor, multiplied by a complex exponential where the exponent is sigma plus j omega. Oh, I remember those. Times our discrete variable n now. And if I have a u of n, it's causal. If I look at this with a little bit more closely, we recognize that this front end part is nothing but a real exponential that's growing if this sigma is greater than 0 and decaying if sigma is less than 0. And this complex exponential breaks up by an Euler identity into a cosine and a sine term, where the real part of it is a cosine, the imaginary part is a sine. So these are providing oscillation. This is providing, again, either decay or exponential growth in the amplitude of the cosine and sine. Okay. Okay, a couple ways I can classify signals, and this will get to your question about causality. We have a left-sided signal, means there's some value at which all points in that signal are 0 for indexes n greater than some value alpha. Therefore, it goes on, maybe it stays non-zero all the way towards the left. It's right-sided if I can define some beta for which all the indices before that are 0. Causal would be a special case of a right-sided function where that beta has to occur at n equals 0 or later, so that the main thing is every value of the function for indices less than 0 must be always 0 to be a causal function. The anti-causal is just the reverse of that. Come on. We take the causality and flip it around, and we have to have values of 0 for n equal to 0 and all the ones after that to be purely anti-causal. Notice this also counts as a causal signal even if it doesn't start till sometime later. That's still causal. I'm always going to look at the negative indices to make sure they're all zero, determine if it's causal or not.
Wouldn't anti-causal be less than 0?
The function has to be 0 for all n starting at 0 and going beyond that.
Because causal has a 0 value at 0.
Right. Causal's allowed to.
Anti-causal should have any value.
Right. Be strictly anti-causal. We have symmetries, just like back in the good old days, even symmetric and odd symmetric, where even symmetric means you've got kind of a mirror image around the n equals 0 axis. So x of plus n is the same as x of minus n. X of plus 3 has got to be the same as x of minus 3. Odd symmetric also is a mirror image, but with a flip to the negative side. So here, for example, x of alpha has to be the negative of x of minus alpha. They have to be opposite sign, same amplitude. The odd symmetric, and that has, for a function to be truly odd symmetric, that has to be true for all values, which means in order for that to be true at 0, it has to itself be its inverse, so that the only thing that it's allowed to be is 0. Periodic signals. Well, the meaning we're seeing a repeating pattern in the amplitude, the sample values in our signal. They must exactly repeat, not just be close, but they must exactly repeat. And the mathematical definition, or the test to see if a function is periodic, is if it has a period of n, capital N samples, then it should be true that x of n plus any integer multiple of that period has to be exactly identical to what it was back at the origin. So they must exactly match when I use 1 times n or 2 times n or 3 times n advance through the signal. If that's true, then it's a periodic signal. And capital N is the period number of samples, and it's always an integer for a truly periodic discrete signal. It has to be some exact number of samples for that periodicity to remain. Periodic signals then give us another way that we can show them. Since they repeat, it's possible to display them using what we call a circular display, where I have a circle with as many notches as there are samples in one period. And by implication, if I give you those samples, I've told you everything you need to know about the signal, except maybe where 0 is. And once I know that, then I know the signal just keeps on repeating over and over and over and over again. So it's a kind of a shorthand way to show a periodic signal. And it's helpful when we get to talking about circular shifts and circular convolutions. It becomes a convenient notation or convenient display way to look at those periodic signals. Question? Usually we go clockwise. Usually we go counterclockwise. Actually, it's not a convention that I actually use very much. Dr. Navi likes it a lot, so okay, that makes sense because of the way we follow unit circles, and okay, I'll buy that. Where we do phase, yeah, okay, I like counterclockwise works. Thanks, good question. And yes, I think by convention the point over here is understood to be the origin. Okay. Different measurements that we can do. Remember these from 228? We can have signal areas, absolute areas. We were wondering whether signals were absolutely integrable or not, and that had some physical significance for the stability of the system. Well, we have parallels to those in discrete time systems, except those integrals become sums. So if I simply sum up the value of some time function or some discrete time function over all indices n, I get the discrete sum, literally the sum of the sequence. It would be every individual sample just all added up. The absolute sum is the same thing, except I'm going to take the absolute value of all those functions, of all those samples, I should say. And a signal is absolutely summable, just kind of analogous to absolutely integrable, if I can literally add up the absolute value of every sample value in that signal and get a finite number. So what we're looking at is a function that probably has to go to 0 in both directions at some point so that I get a finite sum out of it. That would be an absolutely summable signal. Cumulative sums are a little bit different. Here we're summing something up from, well, either some starting point to some ending point, or from minus infinity up to some particular point k. So I'll just keep adding up values until I reach the k value of interest and stop the sum there. So it's kind of like a partial summation of an absolute, well, not even absolute sum, a discrete sum up to a certain level. So the cumulative sum is a function of k. It changes. If I increase k, then I add another term or add some more terms. So this itself is a discrete time function. We can define the power and energy in a signal similarly to how we did back in continuous time systems. Instead of integrals, we're going to use sums. So the signal energy, we're going to take the magnitude of the sample values, take those squared, and add those up. And if we want the total energy in the signal, we have to do that over all indices. If I have a periodic signal, then we can define the average value over one period for that signal by simply summing them up, assuming it has a period of n samples. I'll sum from sample 0 to n minus 1, so I get one complete period, add them up and divide by the number of samples in that period to get the average value. Signal power, then, is the average energy per period in a periodic signal. And so we'll do similar kind of summation over one period from index 0 to n minus 1, or we can use any indices that include one complete period, one complete cycle of the periodic signal. But here we'll add up the magnitude squares of the sample values and then divide those by the number of samples to get the average energy per period. How are we doing? Okay. Simple operations on discrete time signals work like they did on continuous time signals. Just got to be a little careful. If I want to do addition, which we'll represent schematically using an adder block like this. So if I have an x of n signal coming in here, an x2 of n signal coming in here, and the output is y of n, that's the sum of those, that addition is implied to be addition on a sample-by-sample basis. So we're going to add the samples of x1 and to the same indices as those samples in x2. Ooh, how did he say that? So for example, here's an ordered list of x1 sub n. Here's my n equals 0 term. If you ask me to add this to x sub 2, I have to make sure that I line up the indices, the n equals 0 indices, so that I'm adding consistently index 0 to index 0, index 1 to index 1. So I'll have to shift this guy over. Now, if y of n is the sum of those two, I'll add all the n equals 0 terms, all the n equals 1 terms, n equals 2, n equals 3. So I've got to make sure I've got things lined up right in discrete time, because again, we've kind of lost track of time, and that index 0 indicator is the thing that nails us down. So addition implies sample by sample. Question? If we didn't use uh, the dot notation, and particularly if I begin and end with zeros, it's usually a fair assumption that the signal's gone away to zero. And so that's clearly the assumption I'm making here. Multiplication by a scalar, so if the output is a, what question? Why did we? Why did we lose the zero? Oh, so you're saying there should be a zero out here. So with my notation, this is implying there's zeros prior to this too, so I'm kind of okay. It would be better. Oh, we just didn't lose the one on the end. Oh, so we, yeah, because I'm inconsistent. I'll warn you, that's personality flaw. Yes, thanks. That should be consistent on that. Put a zero out in front, that would help. Multiplication by scalar constants works just as you'd expect. We represent multiplication schematically using, well, it looks like an amplifier, where the multiplication factor is inside that. And again, this notation implies that we're going to multiply every sample value by that same constant. No surprise there. So if x of n is this sequence of values, then a times x of n is literally multiply every value by that scalar constant. But you knew that. Okay. Time shifting. We're getting interesting. We draw schematically a shift using a block like this, a delay block. A square block with a z in it, a z and a minus exponent. Well, where the number here is the number of sample values, the number of indices that I'm going to delay. And so the minus is assuming we're going to delay something, meaning shifting it to the right. If I have a z to the positive exponent, that means I'm shifting to the left. So if x of n goes in, what comes out is x of n minus 1, the sequence delayed by one sample. So if I create the output as some x of n minus k, where somebody's got to tell me what k is, any particular value, it would be a block like this with a z to the minus k in it. And what comes in might be x of n. What comes out is x of n delayed by k. Or again, a k is a number of samples. So if k is greater than 0, we're shifting to the right. We're delaying by k samples. If it's less than 0, we're shifting left, just like you're familiar with from continuous time. So, for example, if we define k equals 2 going into this block, and here's my x of n with an index 0 there. We look at the indices. If we write the notation, if this is n, what's n minus 2? Well, we would subtract something from every index. And now we would align x of n minus 2 is going to be 3 where its index is 0. So we would shift everything over that way. Take this whole function, shift it over by 2, 1, 2, to create our new sequence. However, the starting index value here for this function, which is now y of n, would be over here. Okay, so we literally shifted it over by two samples. Okay. So if we have an x of n minus 2, we're going to shift to the right. X of n plus 2, we're going to shift to the left by 2. So here we move that way, here we move that way. Time reversal is folding around the n equals 0 axis. So if this is my original signal, x of minus n is that literally rotated around one time the n equals 0 axis. So we've folded it, we've flipped it around. So if this started at minus beta over here, now it ends at plus beta up here. Now again, the last trick, if I put together a time shift and a reversal, same problem we had in continuous time systems, what order do you do it in? My recommendation, do the shift first. So if this says x of k minus n, do the shift first, then do the reversal, and life will work out for you. Otherwise, you've got to do the, if you do the time reversal first, you've got to shift the wrong way than to what the time shift implies. So don't do that. And here's kind of the proof of that. If we have a sequence with these indices and these values, and I want to find out what value goes into the shifted and flipped version, well, I would look at the indices and match those up and come up with the values of the function. And I'll pause there while you get that in your notes, and we'll pick up on the rest of that on Friday in our new location and move on to talking about periodic signals and what periodic sampled signals look like, because sometimes when we sample them, we can take periodic signals and turn them into non-periodic signals, non-periodic discrete time signals. So we'll look at that and see you on Friday.